any mass has a gravitational field around it. Um, if you look at the Earth, for example, all these arrows pointing towards the center of the Earth indicate the path another mass, a smaller mass, would travel if released from the Earth's surface. There's a gravitational force acting on any mass, and it will accelerate towards the Earth because of the gravitational force. The collection of all the paths that a mass would travel if released is called the gravitational field. So the big M is the field mass, and the little m, smaller mass, is the test mass. Now for electric fields, every charged object, whether it's plus or minus, has an electrical force field around it called an electric field. And by definition, it's the set of all the paths that a positive test charge would travel if released above the field charge. So that field charge is called big Q, and the test charge out here that's released above the field charge is called little q. Big Q being the field charge, because his field is so much bigger than the small q, which is the test charge. Okay, so the arrows extend outwards because the field lines, as they call them, extend outwards because positive repels. A positive test charge is repelled by a positive field charge. In the same way, the test charge is always going to be positive. Okay, and the field charge could be plus or minus, big Q, little q, the test charge. So the direction of the field lines around the negative field charge are always directed towards the center of the field charge. Okay, so that's what fields are. Fields are invisible force actors. They produce a force that surrounds either a mass, if it's a gravitational field, or a charge, if it's an electric field. So here's Coulomb's law again. The big Q stands for the field charge, and the little q stands for the test charge. And of course, F is electrical force between them, the Coulomb electrostatic force between the field charge and the test charge. R is the distance between them squared. So here is the equation for electric field strength, or just plain old electric field. So E stands for the strength of the electric field, or the electric field. And to find E, you just It's the electric force divided by test charge. So there's one equation for finding the strength of the electric field around a field charge at the location where the test charge is. So it's equal to the electric force between wherever the test charge is in respect to the field charge divided by the field charge. So the electric field strength at the location where the Q is equal to the electric force between Q, big Q and little q, divided by little q. That's one equation for field charge. And you can see that the units are newtons per coulomb. Now, electrical force is using Coulomb's law, big Q, little q, times the Coulomb's constant divided by the distance squared between the two objects, the two charges. Okay, we can substitute this in for this F. So we can come up with a different equation for E. E equals F, which I'll substitute for this Coulomb's law for F, divided by Q. And you can see that the Q's cancel, the little q cancel out the test charge. And so we're left with a new equation for E. If you know the field charge, big Q, and you know the distance between whatever location in the field you have, so you really don't need little q, because look, here's big Q, and you could just have any location. And if you know the distance between that location in the field and the field charge, then you know the field charge value, you could just use that equation without having a test charge at all to measure the field. So there's two equations for electric field that you can use depending on what given terms you have. So here's 4 rules about drawing electrical fields. So the first rule just is stating that if you have a positive field charge, electric field lines point away from the positive field charge, assuming that the test charge is positive as well, which we always do. And if you had a negative field charge, the field lines end on the negative field charge, because that's the way positives are attracted to negatives, and the test charge is always positive. Okay, rule number 2, the density of electrical field lines. Now, when they say the density of electric field line distribution, that means the closer the lines are to get to each other, the more densely packed they are, the stronger the field around the field charge is. So if you had something like this, and you had something like this for a Q, let's say one points there, and this one points away. It doesn't really matter. Okay, so what charge would be, according to the first rule, what charge would be the field charge on the left? Well, Q is positive, so it's being repelled, so that would have to be positive. And the field charge on the right one, test charge is always positive, because those test charges are attracted towards the field charge. The field charge would have to be negative. But anyway, rule 2 is pointing out that, notice that this, let's make a little box here, just same box here, in that same area, at the same distance away from the field charge. The box on the left has more lines in it than the box on the right. So this would be a higher density of field lines at a certain distance at a given R from the field charge. So we can higher density of lines means a stronger field, a bigger E. And that would represent larger field charge. Larger Q, big Q, little q doesn't matter. And then rule 3 just states that these lines, these field lines, never intersect with each other. Okay? They just don't. Okay, number 4, lines are continuous. It means they continue out infinitely far if they're not bent by some other large field charge. So this picture is just reminding us that it's not just two-dimensional. The field is not just 2 dimensions in a plane. It's 3-dimensional. It's coming in all directions towards or away from the field charge. This picture is simply showing that if you take a circle here and a circle out here, same size circle, as a radius, as a distance away from the field charge, increases as R increases, the field out there would be smaller. Field gets weaker, just like a gravitational field gets weaker as you get further from a mass. So here's the 2 equations for electric field around a field charge. Okay, so I want to key in on this one. As the distance away from the field charge increases, the electric field decreases. So we can say E is inversely proportional to the distance you are from the field charge squared. So my questions I could ask would be, if I doubled the distance you are from a field, okay, so if I went from here to twice as far, I double the distance. How's the field out here compared to the field here? Well, you can look at this equation right here instead of the proportionality equation. I mean, instead of using that, you can use the actual equation. So if I put 2 there, what happens to the E? It goes to 1/4 of what it was. Okay, so that's a good what-if question. Now out here, the density lines are, let's say, a circle like that. The lines are denser out in the where you're closer over here. You got 2 field lines in this location compared to 1 field line in this area right there. Okay, so you can just look at the picture and say the closer the lines are, the stronger the field is in that location. So we're supposed to find the electric field, E, for charge. Okay. I guess this is the field charge right here. So that's big Q. At a distance of 3 meters, that's R. Okay, so they gave me nanocoulombs for this, so I'm going to have to remember nano is e to the negative 9. I'd give you that on the test. So let's solve the equation. Would be what? K big Q over R squared. So K is 9 e to the 9. That's Coulomb's constant times the field charge, 5.6 e 10 to the negative 9 divided by 3 squared is 9. So basically, I don't even need a calculator because 10 to the 9 times 10 to the negative 9 is 10 to 0. So these guys cancel out too. And so that leaves 5.6 newtons per coulomb. Okay, this one, they have little q, the test charge, experiences an electrical force. Okay, so that's the electrical force in the presence of an electrical field. What is the size of, how strong is the electric field out there? So this case, we're going to have to use force divided by Q, test charge, because they didn't give me the field charge or the distance, so we use the other equation. So the force is millinewtons, so that's 9 e to the negative 3. That's what milli stands for. And then the charge is also millicoulombs. So I didn't really have to change it because that would have canceled out. So that's 4.5 e to the negative 3. And so the negative 3's, 10 to the negative 3 cancels out. 9 divided by 4.5 is 2 newtons per coulomb. Okay, this one. So E, distance R. What is the electric field? Okay, so if I double the distance, what happens to the E? So I'm going to have to use this equation for E. So if I double the distance, what happens to E? Well, 2 squared. In the denominator, it goes to 1/4 of what it was. It was EO. Now it's 1/4 of what EO was. Okay, at point A, the field is E. What is the electric field at point D? So what's E at D? Well, it's 1, 2, 3, 4 times further at D compared to location A. So the distance at D equals 4 times the distance at A, right? So we're using our equation again for E. I'm asking what's the E, the electric field at D compared to the electric field at A. So E equals KQ over R squared. Okay, so it's the same as the last problem we just did, so I'm going to put a 4 there because it's 4 times further at D. So I had to bring 4 squared in the denominator, so it's 1/16 of what it was. Okay, the electric field at a point in space. Okay, so let's say we have some field charge, and there's a point in space around that field charge. It's defined as perpendicular to the direction that a positive test charge will accelerate. Okay, so it's either going to accelerate towards the center or away from the center. It's not perpendicular. It's on the path directly to or directly away from the field charge. So it can't be perpendicular. Direction that a positive test charge would accelerate. Yeah. So remember, the test charge always is positive. And if you release it, it's going to either accelerate away from the field charge or directly towards the field charge. Directly away or directly towards. So B is correct. It's not a negative test charge. That could happen. If I put a negative, it would accelerate. But by definition, the direction is for a positive test charge. So that's the direction of the field charge. So C would give you a backwards arrow to what the convention is. So skip that. Well, the test charge is always positive. So away from the field charge, which is a big Q. And all these arrows will be the same because they're all the same distance apart. So 1 up, right, down, left. Consecutively, respectively. 1 would be up, 2 would be right, 3 would be down, 4 would be to the left. So remember, Q has to be positive, so this would be down to the left, up to the right, down, left, up, right. So that would be the direction of the field line. Also, as we should point out, the direction of the field line is in the same direction as the direction of the force, electric force. This table is going to compare electrical field and gravitational fields. Okay, first of all, look at the equations for gravitational force and electrical force. They're very similar. Like we said before, they have different constants. Okay, big G for gravitational force and little k constant for Coulomb's law. Instead of masses, we use charges for Coulomb's law. And for Newton's universal law of gravity, we use masses. Okay? But the distance, the proportionality of the force to the distance between the two objects squared is the same for both equations. Gravitational field, we know that. You should remember a gravitational field is acceleration due to gravity. And we talked about that equation in the gravity unit. And see how it's so similar to electric field. Okay, instead of big G, we use little k. As I said before, instead of the field mass, we use the field charge, and we got r squared. So we got these interesting similarities between gravity and electricity. So let's answer this one. How are gravitational electrical fields similar? How is G and E similar? They both increase. No, they both decrease the further you get. They both decrease as a factor of the square of the distance. Yup, that's true. Letter C is kind of true, but not as precise as letter B. So it's just as a factor of the distance squared. So they left it out, so that's not right. The fields are constant throughout space. No, as you get further from the object, the field decreases, so that's wrong. Okay, so how are they different? Two answers. Okay, little g is much stronger than electric field for the same kind of masses or charge. No, because if you look it up, k is 9 e to the 9, whereas big G is tiny. What is it? 1.6 e to the negative 19. So, because that constant is so much smaller, 1.6 times 10 to the negative 19 is so much smaller. So if you look at the equation for electrical field, it would be K big Q over R squared. The equation for a gravitational field is big G big M over R squared. So because big G is so much smaller than K, K is so much bigger. 9 times 10 to the 9 compared to 1.6 times 10 to the 19. This makes electric field for a Coulomb much, much bigger than the gravitational field for a kilogram, around a kilogram. So we can say A is false. Okay, reading choice B. Masses in a gravitational field always feel a repulsive force. They never feel repulsive force. Gravity is always attractive. Electrical force could be repulsive or attractive. So C and D have to be right without me even having to read them, but let's read them anyway. So mass in a gravitational field always feel an attractive force, whereas charges in an electric field can either feel an attractive or repulsive force. Okay, so that's obviously true. The gravitational field is much weaker than an electric field. That's explained when I showed why A is false. Okay, so we have an electron next to a proton. Now their masses are tiny, tiny, tiny. And because what we said before, big G is so much smaller than the K constant, Coulomb's constant. So therefore, the electrical attraction is humongously greater than the gravitational attraction between these two. There is a tiny gravitational attraction, but it's pretty insignificant compared to electrostatic attraction. Now, if you have two field charges next to each other, those field lines are going to get distorted because the influence of one on the other will be obvious. If the cube, the little q, is really tiny compared to the big cube, we don't care about any distortion to the big Q's field. But if the two charges are, close to being relatively the same size or not a huge difference in their magnitudes, you're going to get the field lines being bent. The field rules still exist that I talked about before. The field lines, they keep on going in space. They're going away from positive towards negative. They never cross. Yeah, so you get this kind of bending, and it looks kind of like a four-way intersection if they're both the same charges. So you should recognize that in these two negative ones on the bottom and the two positive charges, the field on the top, the field lines make this like intersection, this four-way intersection, where it's like the field lines are getting pushed by either one, by either charge. Now, if you have unlike charges, you'll have the field lines doing something like this with like a mitotic spindle effect. So we can see here there's no places that the electric field is zero. If you look at the previous picture, I should have said that. There's no electric field lines in between the two like charges. But here, you have field lines anywhere between them or around them. But when you have two like charges, the field lines, remember, go like that. I should have shown you that before. Right in this space right here, you'd have no field lines, so there'd be no electric field there. Also notice how the rule that the field lines have to come out of positive and go towards negative still apply. Okay, two negative charges is repulsive. So only is that four-way intersection kind of thing. So it has to be this. Now, they should give me another choice to make it trickier, like that, but with the lines going outwards. Okay, but they didn't, because that would have confused you probably, maybe. So if these were positive, the arrowheads would be going outward, but it'd be the same picture as that. So this letter E. Okay, so this would be positive and negative charges. That's attractive. And so it'd be that spider web kind of thing. And notice they made this easy, but they should have given you another choice where the arrowheads are going the wrong way. But remember, field lines always come out positive and go into negative. So letter B is right because of that spider web thing between them. We have two parallel plates, charge plates, and we hook up a battery, okay? In fact, this is a battery. Okay, a battery consists of two terminals, a plus and a minus, and they're connected to two parallel plates. One has inside the battery. One has positive charge on it, and the other has negative charge on it. And the charges are the amount of charge, positive charge on one plate is equal to the amount of negative charge on the other plate. So we call this a parallel plate. What's important here is that the electric field is uniform. You see it right here. The density of the lines are the same no matter where you are between the plates. So the E will be uniform between the plates wherever you are, same value. But the electric field outside the two plates is zero. There is no field lines outside the area between the volume between the two plates. So if you put a little positive test charge in there, Q, which direction would it move? According to the field lines. If you put a negative, like an electron there, it would move up opposite to the field lines, just like for a non-uniform electric field. Same thing. Okay, this is just reinforcing that around the point charge, you have a non-uniform field. The E decreases as you get away from the charge, but in between two plates, the E stays constant. So I'm not going to use this equation for parallel plates because this would show that as I get further one plate, the E changes, would decrease. So only do that with point charges, like dots. Okay, but we can use this equation for parallel plates or point charges because the distance doesn't have anything to do with finding the electrical force on test charge between the two plates or from a point charge. So here, a neutron is no charge, a proton is plus charge, electron is negative charge. Which of these particles experience the most electric force the least? The equation for a field is F over Q. So they're looking about for the force, electric force. Well, E's constant doesn't have to do with the charge at all, the point charge. E is constant. I haven't given you the equation for E between two parallel plates, but it's constant, it's uniform, so I don't need that detail yet. Okay, so Q of a neutron is zero. There's no charge, that means charge. So the neutron would be the least. The force on the neutron would be the least of them all. And isn't the charge of electron and the charge of proton the same magnitude, but different signs? So one's plus one, one's minus one. Now I can change that to coulombs, but why? No need. So that means the force on the electron, because of the field, would be equal to the force of the proton in the field. Okay, so we already figured out that the force is the same on both the proton and electron, but the electron will be accelerating towards the positive plate, and the proton will be accelerating towards the negative plate. But you should remember that the mass of a proton is about much bigger, 2,000 times the mass of an electron. Or just know that proton is much more massive than electron. So because they have the same force, because of Newton's second law of motion, if you have the same force, but you got a much bigger mass, your acceleration is much smaller. So the acceleration of the proton would be like that if I were to draw a vector, whereas the acceleration of the electron would be 2,000 times bigger, like that. So here they explain what I just did. It's a very important question. So the negative plate's up on top, the positive plate's on the bottom, and we got 3 electrons at different distances. Now, a lot of people get this one mixed up. Okay, first of all, a lot of people think, ooh, the one that's closer to the negative plate is going to have a bigger repulsive force than the others. Don't even think like that. Go to the equation. E equals the electrical force over the charge of the electron in this case. So the E is the same for all 3 of those things. The Q is the same for all 3 of them. -1, but in coulombs. The F would have to be the same for all of them if E and Q are the same. E is the same because it's a uniform field. Q is the same because they're all electrons with -1 charge. So F has to be, the electrical force has to be the same on all 3 of these. Okay, so we have a charge. Okay, so milli means 10⁻³ coulombs. The electrical field E is this. What electrical force will it experience? Okay, they don't ask about the direction of it. So E equals F over Q. So rearrange the equation. So you're solving for F. F equals EQ. So do the math. Let's see. 3 e to the 3 times 6 e to -3. Well, E3 times E -3 is 10 to the 0, 1. So it's 3 times 6 is 18 newtons. Okay, so we got a charge. Q equals 2e to the -6 coulombs. That's what micro stands for. We don't change kilograms. That's the mass. We want kilograms. This is the only unit we use that has a prefix that we need to keep when we're doing equations with it. Here's acceleration, the magnitude of the field. Okay, so I'm looking for E. E equals F over Q. And you're going to say, wow, I don't have force. But don't give up. You do have the force, or you can find it. Because the net force is the force, because weight's not significant. And that equals MA. So I can substitute MA in that equation up there. Then I'm solving for E. I don't have to cross multiply, I just substitute in. the mass is 0.0001 times the acceleration is 4 divided by Q. Q is 2 e to the negative 6 coulombs. Now, you really don't need a calculator. You could, but this would be 4 e to the negative 4, because 0.001 is 10 to the negative 4 divided by 2 e to the negative 6. So we get 2 e to the negative 4 minus the negative 6. I'm using my exponent rules. So that'd be 2 e to the 2 which is 200. So 200 newtons per coulomb. Okay, they could have drawn a picture here. So I just did. So we have a small particle of mass m. So significant. The mass is significant. Okay, so we would have a weight vector downwards. So it's that equals mg. Okay, well, the electric force would have to be upward in this case. So if it's going to levitate, the electrical force would have to be upward equal to the weight. So if I had been given that picture, what would attract a positive? So the charge on the particle has to be negative. Now if it was flipped around, if they had given you a picture like this instead, here's the mass. The mass has weight down, and the electrical force would have to be opposing that weight, so the charge would have to be positive. So if they had given me this picture, it would have been that. If I had given that picture with the plate being positive on top, it would have been that answer. Okay, again, I don't see a picture, so it doesn't really matter. I could have either one of these situations that I had before. Okay, here's the mass. Okay, here's the weight, and here's the electrical force. Okay, weight equals mg. Electrical force equals QE, like I had in the previous problem, because E equals F over Q. So I'm looking for Q. So I know that FE equals QE, and I know that the weight equals mg. I know that if it's levitating, these two forces have to be equal. I mean, weight and electrical force. So I can do mg equals EQ or QE. So what am I looking for? The charge. Q, divide both sides by E. mg divided by E. So let's choice B.